Here we are going to study the motion of a charged particle in a uniform electric field. So first of all, we are studying when the particle is at rest. So I am considering a charged particle of charge Q and mass m, which is in this uniform electric field. So this particle will experience a force due to this field, and that force F is equal to Q times E. But we know that the force is mass into acceleration, so that will be equal to QE. So that acceleration experienced by the particle is QE by M. But in vector form, we can say that A is equal to Q into vector E upon M. So this is the acceleration. And we can say that if the charge is a positive charge, then the acceleration will be in the direction of electric field. And for a negative charge, the acceleration will be opposite to the electric field. So A will be in the direction of field for Q is equal to positive and opposite to field for Q is equal to negative. And we can also find the velocity of the particle at any time, and that can be given by Newton's equations of motion. So velocity v is equal to u plus at, but the initial velocity is 0 because the charge is at rest initially. So the velocity can be given by QE by m times t. So this is the velocity acquired. And we can also find the distance traveled. The distance traveled and that will be equal to ut plus half at square, but initial velocity is 0, so that half into acceleration, that is QE by m times t square. And we can also find the kinetic energy gained, that is equal to half m v square, and that will be equal to half m v is q square e square by m square times t square. So we get that q square e square t square by 2m. And now we are going to study the motion of a charged particle when it is entering to an electric field in a perpendicular direction. So let me consider a charge of plus q, and let this is entering to the field in perpendicular direction with an initial velocity u. So whenever it enters to the field, it will experience a force due to the electric field, and so that its velocity in the direction of field will be increased, but there is no force in perpendicular direction, so that the velocity in perpendicular direction will always be a constant. And due to these two velocities, this particle will traces a path like this, and we are going to study the motion of this particle. And for that, for simplicity, let me consider a two-dimensional coordinate system because this is a two-dimensional motion. So let this is x direction and let this is positive y direction. So I can say that the initial velocity in x direction, that will be equal to u, and similarly the initial velocity in y direction, that is 0, because the charge is entering perpendicular to the field. And similarly the acceleration in x direction, that is 0, because there is no force in x direction. But the acceleration in y direction, that will be qe upon m, that is due to the force exerted by the electric field, and which is in the direction of electric field for positive charge. And once we have these quantities, we can find the displacement of the particle at any point, and that can be given by the Newton's equations of motion. So I can give the displacement in x direction, that is equal to uxt plus half ax t square. But acceleration in x direction, that is 0, so we can say that ut, or I can say the time, that will be equal to x upon u. Let me call it as equation number 1. And similarly the displacement in y direction can also be found, that will be equal to uit plus half ayt square. But in y direction the velocity, initial velocity is 0, so we can say that half ay is qe upon m times t square, that will be equal to half qe upon m. I can substitute the value of t from equation number 1, that will be equal to x upon u whole square, or this will be equal to qe upon 2mu square times x square. So here the charge is a constant, the electric field is also constant, the mass of the particle is constant, and the initial velocity is also constant. So we can say that y is proportional to x square. That is, the displacement in y direction will be proportional to the square of the displacement in x direction. So this is an equation of parabola, right? So we can say that the trajectory of this charged particle will be a parabola. We can write that the trajectory will be a parabola. And now we can find the velocity at any point. So this will be the trajectory of this particle, and at any point we can find the velocity of that particle. Let this point is x comma y. I can find the velocity at x, so that we can find the velocity at any point. X comma y. For that we can use the first equation of motion, that is Vx is equal to ux plus axt, and ax is 0, so Vx is u. So the velocity at any point in x direction, that is a constant, that is u, and similarly the velocity in y direction, that will be equal to uy plus ayt, and uy is 0, so that will be equal to ay is qe upon m times t. So we can substitute the value of t from equation number 1, that is x upon u, that is qe upon m into x upon u. So this is the velocity in y direction. So once we obtain the velocity in x direction and velocity in y direction, we can find the velocity at any point x comma y, that is v is equal to under root of, that will be the vector sum of these two velocities, that is vx square plus vy square plus 2 vx vy cos theta, but the angle is 90 degree, so that term will be 0. So that will be equal to u square plus qe x upon mu whole square. So this will be the velocity at any point. Now we can find the velocity when the particle leave the field. So let this is the width of field L. So the velocity, let L be the width of field, then the velocity of particle at the point of escape will be, that is the velocity at the point of escape that will be equal to under root of u square plus qe, in place of x L will come, so qel upon mu whole square. So this will be the velocity of the particle when it leaves the field. So whenever it leaves the field, there will no any force, because there will be no field. So it will leave the field in a tangential direction to the parabola at the point of escape. So let this is the angle theta, so it will leave the field at an angle theta, and which is tangent to the parabola, and we can find the angle by finding the slope of the curve or the slope of the parabola at the point of escape. So we can say that the particle will leave the region or the field in the direction of tangent to the parabola at the point of escape. And that can be given by tan theta is equal to dy upon dx at the point of escape, that is L comma y. So we have already find the y, which is qe upon 2mu square x square. So d by dx of qe upon 2mu square x square, but this is a constant, and qe upon 2mu square d by dx of x square, which is 2x, and that will be equal to QE upon mu square. But the point of escape, the x will be L, the width of the curve. So this will leave the this will leave the electric field at an angle theta, which is given by this angle tan theta. And we can also find the kinetic energy of this particle at the point of escape. That will be equal to half m Vx square plus half m Vy square. So the kinetic energy, that will be equal to half m into V square, that will be equal to U square plus QEL upon mu whole square. So this will be the kinetic energy. And we can also find the work done by the electric field. That will be equal to force into displacement, or that will be equal to the change in kinetic energy. We can write whatever it is. The work done by electric field, that will be equal to force into displacement, force into displacement. Force is, we know that it is QE, into displacement, that will be equal to QE by 2mu square x square. QE by 2mu square x square. In place of x, the particle will leave at L, so L square. So that will be equal to Q square E square L square upon 2mu square. So this will be the work done by the electric field on that charged particle. Thank you.